Today I will not speak at all about CoRoT and Kepler, but about results from Spitzer and MOST satellites, which are also part of the space photometry revolution. I will present the Spitzer and MOST transit analysis and also the modeling of the O star from classic methods and from asteroseismology. It's a work that I have done with these people, and especially my colleague Michael Gillon from Liège. So HD 97658 is the second brightest star harboring a transiting super-Earth. So it's very important to characterize the exoplanet and especially its atmosphere. The brightness of the star is an important parameter. So it's a K1 star. The O star is a K1 star with an effective temperature slightly higher than 5,000 K. It's underabundant for the iron abundance, and I have no other metal abundance, so I simulate this to the metallicity of the star. And we also know the distance of the star from Hipparcos. About its transiting super-Earth, this planet was discovered by Howard et al. From radial velocities with the Keck telescope, with a minimum mass of about 8 Earth mass and an orbital period about 9.5 days. And the transits were discovered with the MOST satellite last year by Dragomir et al. 2013. I don't have to recall that we must know very well the O star to characterize the exoplanet. And especially here we have both transit and radial velocities. From the transit, we can derive the radius of the planet, which is directly proportional to the radius of the star. And from the radial velocities, we can derive the mass of the planet, minimum mass of the planet, and it's proportional to the mass of the star exponent 2/3. And also the age of the star, the best proxy, the best way to determine the age of its planet, because a star and the planets are formed more or less together. The best method to have the stellar mass reduced in age is asteroseismology, and we had a nice example during this meeting. But for that star, I don't have asteroseismology because it doesn't fall on the fields of CoRoT or Kepler. So I have to deal with classical stellar evolution modeling. This is the following. From the distance of the star and its apparent magnitude and some bolometric correction, we can derive the luminosity of the star relatively accurately because the distance is very accurate. And combining this with the effective temperature from spectroscopy, we can derive a quite accurate stellar radius. To have the mass and the age, we have to rely on stellar evolution modeling. And for here, I use the Liège stellar evolution code CLE. And using as input the luminosity, the iron abundance, which I took for the metallicity, and the effective temperature, we can derive a mass and an age. For low mass stars like HD 97658, we can be relatively accurate on the stellar mass. And here I took into account the uncertainty on the helium content for that star. Helium content cannot be, it's a major uncertainty in stellar model, and it cannot be inferred from spectroscopy. We must have asteroseismology to constrain this. But for low mass stars, the isochrone are very close to each other, so we have no constraint at all on the edge. We can cross the luminosity effective temperature box at any age. About the Spitzer observations, it's warm Spitzer IR camera at 4.5 micrometers. It's warm Spitzer because it's not cooled anymore since many years now, but we can still use it in the near infrared. It's part of the program that we have in Liège to search for transit for low-mass planets found in radial velocity. So it's exactly the goal, also the goal of CHEOPS, to measure, to search for transit, so to measure the radius of planets for which we already have the mass. I will explain later what we can infer from these two parameters together. So we obtained a 6 hour on Spitzer last year, and 6 hours after following the MOST ephemeris. So we had to trust the MOST ephemeris to have the transit. In blue, you have the raw data from Spitzer, and I agree that they are quite scattered, but Spitzer is very well known since many years now, so we know the instrumental systematics of Spitzer very well. So we can have a quite accurate photometric model, and by subtracting this systematics from Spitzer to the raw data, we can really see a very beautiful transit and exactly where it should be, exactly 17 orbits after the last MOST transit. So Spitzer fully confirms the MOST ephemeris and the existence of this exoplanet. I will go very fast on that because it's not the first time that we speak about MCMC this week. I used the Liège MCMC code to characterize the exoplanet. For the jump parameters, we have two kinds of jump parameters, which are those for which the chain is varying. Those for which we have no information a priori, so they have uniform prior distribution, and the others for which we have information. So we put a Gaussian prior distribution. It's just basically the stellar parameters. From that jump parameters, we can build a model, a transiting model, to be compared to the data for a main function, a usual main function, plus a Bayesian penalty for jump parameters that have a Gaussian priors. And as a result, we have probability density function for each jump parameters, and from that we can derive the physical parameters, like the planet mass, radius, and so on. These are basically what I used to analyze together the 171 Keck radial velocities, the one transit from Spitzer and the 3 transits from MOST. And so here the jump parameters, so transit depth and orbital period. And from that we can derive the planet and also stellar parameters and the mass, the radius, the mass at Spitzer wavelength, but also invisible. Semi-major axis, it's a quite close-in planet, and a small eccentricity, as it is the case for most planets, super Earth. Just a word about the uncertainties. We have 5% accuracy on the planetary radius and 11% accuracy on the planetary mass. This comes from the O star. We have 3% on stellar radius thanks to the accurate distance of the star and stellar luminosity, and 8% on stellar mass. And the difference comes from Spitzer and radial velocities systematic. And this is the goal of CHEOPS, to reduce this systematic to have very accurate observation for transiting planet. And so from there, the uncertainties on the planet will come mainly from the star. And to improve the knowledge on the star, the best way to do it is to have asteroseismology. So that's why PLATO will do both asteroseismology and exoplanet on the same targets. And from that, we can have the star and planet parameters within 5%, as Aikaro presented. Just a little word about the importance of accurate stellar modeling. In the paper of Diana Dwagomir, she analyzed the same MOST lie curve, but she derived a less accurate planet radius because for a stellar modeling, she didn't use the stellar luminosity from Hipparcos, but she used the spectroscopic log-G, which is from far much less precise. And it's a good hope for the future that we'll have even more accurate distance from Gaia, and it will allow us to have quite accurate stellar radius, at least. So HD 97658, it's really what we call a super-Earth, an intermediate object between the Earth and which is the biggest telluric planet in our solar system, and Neptune, which is the smallest giant planet. So it's a kind of object that don't exist at all in our solar system. And theoretically, we can have a wide range of composition for that kind of object. We can have true super-Earth, rocky core with a very thin atmosphere. We can have water world, the famous ocean planet. We can have a mini Neptune with an icy core and a very thick hydrogen envelope. We can have a full gas planet, but dwarf. And the key parameters to begin to discriminate between the several possible composition is the bulk density of the planet. For that, you must have the radius and the mass, of course. And this is why CHEOPS and also TESS want to measure transiting planet. For planet, we already know the mass, or we can know it because it's bright target. Here, in that case, we have an intermediate average density. It's exactly the same density than planet Mars, But because HD 97658 is much bigger than Mars, it has a lighter composition. In detail, I have asked to planet composition specialist, Diana Valencia from Toronto, to compute possible internal composition, thank you, for that planet with these effective temperatures. And the result is very interesting. We can say that this planet is mostly rocky, with at least 60% of rock and mass. Water plus ices, and ices mean methane and ammonia. It could be 0% and up to 40%. And the most interesting thing is very little hydrogen and helium component, by less than 2%. So we don't have a true super-Earth because it can contain many water and ice, but it's something that is really intermediate between a true super-Earth and a mini Neptune, so a very new kind of object. About the atmosphere of this planet, we obtain time on the wide field camera 3 of the Hubble Space Telescope. The PI was Peter Knudsen from Caltech, with several band passes between 1.1 and 1.6 micromet, and it's basically to have the water band absorption, which is at 1.4 micromet. As you can see, it's not easy at all to explain this scatter. It's the best, it's the most precise, most accurate measurement that we have so far for transmission spectrum of an exoplanet. So we cannot do better than this, but it's not easy at all to explain. We can exclude a cloud-free solar atmosphere in red, but the only possibility that may be possible is a flat spectrum, but we have to trust that this can be a flat spectrum. And it could be a water atmosphere or solar composition atmosphere with clouds. I refer to the paper of Peter Knudsen. I'm not at all a specialist of planet atmosphere, but just to say that is the best thing we can do today with the current instrument, but it's not easy at all to do that. Back to asteroseismology now, something that I know better than planet atmospheres. What asteroseismology can bring to that stars, especially. I remember that we have a good stellar radius, an average stellar mass from stellar diffusion modeling, and no constraint at all on the age. I computed oscillation frequencies of stellar consistent models, and by consistent I mean that these models respect the hydrostatic equilibrium and that the oscillation code that doesn't break this consistency. And all this stellar model is the one that crossed the box that I showed before, so that respect the effective temperature, luminosity, and high abundance of the observational constraint. And I computed the large separation and the small separation, not from a scaling relation, directly from the pulsation spectrum that I computed at the new max, where the observed pulsation spectrum is expected to be. And I plot large separation versus small separation. It's called a CD diagram. CD is for Christensen and Dalsgaard, of course. It's the same model hypothesis than before, and we can see that 1 microhertz accuracy on the large separation and the small separation will help to get a better stellar mass and age. So it's good news. The bad news is that the star is very dense. It's very at the limit of what we can do from asteroseismology. It's a K1 star, but it's also a bright star. It's a V equals 7 magnitude. So maybe we can hope with PLATO to have asteroseismology one day on that star. So as conclusion, HD 97658b is a key transiting super-Earth because it's an intermediate average, it's an intermediate density super-Earth. And we always wonder for the composition of such object. And here apparently we have something that is really intermediate between a true super-Earth and a mini Neptune, so a new kind of object. It orbits a very bright star, the second brightest star for a super-Earth, so it's very important for future atmospheric characterization, especially with the James Webb Space Telescope. I've shown that with the current facilities, such as the JWST, it's still very difficult. We can wonder about the formation of such a planet because it's a quite close-in planet, so it's probably it's not probably a form in situ. And I have also shown that characterize the O star as essential, and I think is the basic message of this conference. But future observation for this star, we have obtained 3 more transits with Spitzer, but we hope that it will be done before Spitzer will stop, because it's planned to be stopped in the coming months. From Gaia, we'll have a very accurate distance, or luminosity and stellar radius, but it won't be sufficient to have an accurate stellar mass and age, because we still have major uncertainties in stellar models, which are the helium abundance and also the efficiency of convection. We need asteroseismology to do that. CHEOPS and TESS will observe these super-Earths because it's the core of the program of these 2 missions, and we'll have an accurate planet radius and visible. And I'll come back to it, asteroseismic observation. We need PLATO to do that, and from that we'll have a better stellar mass and finally a good estimate of the stellar age. So this is the other message of this conference. Space mission like PLATO will bring a lot to exoplanets and the host stars. Thank you.
Thank you. Questions? Let's start over here. You are not awake, Mikkel. What's
the Hubble measurements.
The what?
The Hubble measurements. Normally, I would suspect these would be systematics of something, except that it seems that this wide field camera for Hubble is quite good, and it hasn't shown many systematics in the other measurements I've seen. So do you know if this, if we suspect this is at least true, or are we worried that this could still be systematics?
They say it is the better measurement that I have had with Hubble. I think the noise is something like 20 ppm, but of course this result, in the paper of Erik Knudsen, they used 2 separate methods to derive the transit depth, and both methods agree very well with each other, so we can be quite confident, but apart that, I don't know very well the detail because I'm not the specialist, but I refer to the paper if you want.
I think the magnitude limit for expected asteroseismic detections with TESS is around I of 7.5. And so it's near the limit, but I suspect you may be able to at least get a detection of the global asteroseismic parameters from that.
Yeah,
and it'll be 5 years sooner, so that might help.
Yeah. For the large separation, yes. For the small one, I don't know.
I think this star is actually too low mass to even, I mean, it's not a solar temperature, so
it's yes, almost
it's okay, so I think it's impossible with TESS.
Yes, I've asked
at
that time, and you say probably not.
It should be tried, of course, but...
yes, we'll try, but maybe large separation, but probably not better, and even if we have a large separation, we still have some uncertainty.
Yeah. Tim?
Yeah, I think the best chance might be ground-based velocities for this star.
With espresso, maybe? I don't think with... maybe we can try with arcs.
Song or harps, or where is it? Sorry, which hemisphere?
Who's speaking?
Sorry,
Tim Benning
is
sitting
okay,
down
sorry.
there.
What's the...
It's the voice from the top.
Yeah, I don't see anything.
Is it north or south? Which hemisphere is it in? What declination?
I think it's in the north.
Okay,
I think it's 25 degrees in the north, I think.
Half north, maybe?
Yeah.
Yeah.
But we have to convince that it may be possible.
The amplitude would be... Any other question? Let's thank Valerie again.
Thank you.